Logic gates. In this presentation, we're going to be looking at what are they and how are they constructed? We're going to look at their symbol identification. We'll then move on to the operation of a NOT gate, AND gate, OR gate, and finally finish off with some timing diagrams. Logic gates are one of the first examples we have in the apprenticeship program of basic computer automation. Logic gates execute an output signal based on the combination of input signals that it receives. In this way, a logic gate applies basic logic. Logic gates are constructed from a specific arrangement of transistors or other types of small circuit components. An integrated circuit is made up of multiple logic gates. So we can see here, a single transistor is used to then make a combination of control, which is in the second bubble where we have two transistors. And those two transistors with that specific connection make up this specific logic gate, which is one of many inside an integrated circuit chip. Now, computers communicate through ones and zeros, which is binary. And these signals in the real world are represented by plus 5 volts, high signal, or 0 volts, which would be a low signal. Now, in definite reality, will they be perfect 5 volts and perfect 0 volts? Definitely no. But this is the general premise we're working on. A logic gate can receive input signals and then decide based on its orientation and how the control design has been set up, it will send out output signals. Logic gates have symbols on paper, and there are three basic types of logic gates: NOT, AND, OR. Each of these logic gates has a unique symbol that represents it. The inner workings of a logic gate are not shown in the symbol, which can lead to a degree of confusion because this symbol down here, a NOT gate, looks pretty basic, but it's only representative of the logic function. It's not really a schematic symbol. And because of that, we need to understand that there is more at play with that particular symbol. And we'll take a look step by step at how this will operate. This essentially would be a full NOT gate circuit. But we're a little bit ahead of ourselves here. A NOT logic gate is made up of a single transistor, a couple of resistors, a DC source connection, an input, and an output. Now, very often on an electronic type of circuit, we will only see the plus 5 volt of the source being applied, but not the negative 5 volts. And that's because on many electronic components, the negative is connected to the circuit board or the chassis, and that represents ground. So wherever we see a ground symbol on a circuit, we can take that to mean the negative side of the DC source. Now, let me be clear. It's not important for you to memorize the schematic layout of this logic gate. Instead, we show this just to give a baseline for what's happening in the logic gate when we start looking at the possible scenarios. Now, very basically, a NOT gate is one where an input comes in to the NOT gate and the opposite type of signal comes out as an output. That means that it's inverted or opposite, and we signify that with a circle at the end of the tip of that little triangle. So that means if I have a positive input or plus 5 volts, the output would be 0 5 volts or 0 volts. Here's what the operation would actually look like. And we can see that when we have no push button pressed down on the left side, that means my base terminal is not triggered and there's no current flowing through the transistor. At this point, the light is on, and that would be a high signal. And we can trace that through by looking at the source. It connects through a resistor and then to the load, and then notice the ground symbol, which means it connects all the way back to the DC source. When we press it down, there's now current that flows through the base terminal, causes the transistor to conduct anode and cathode, which means now there is 0 voltage for this little light to operate, and it turns off. An easy way for us to represent this information clearly for logic applications is with a truth table. Every logic gate will have a truth table, and the truth table is an important, clear feature that allows us to very quickly determine the state of the inputs or outputs. So we can see here from the right-hand diagram that there really are only two combinations. Either the input is low, 0, and the output is high, or the opposite. The input is high and the output is low. The way that we represent this in a truth table is to simply put 1 or 0 for the high and the low. This is an example of an AND gate. It's built from 2 transistors, and what we'll notice is that there are now 2 inputs and 1 output. Remember, the same application of having the ground symbol simply means that we have the negative connection to the DC source. We don't need to memorize the schematic layout of the logic gate, but instead it's used here to help assist in the clarity of the operation. The 2 transistors are set up so that the top transistor feeds into the bottom transistor. And this means that both of them must be conducting in order for the output to go high. What this then means is that if I press one push button down, there is no flow. And that's because, although this one is in conduction now, this one is still blocking. If I press down only A, well, now I got a high signal here, and this one's conducting, but this one's blocking. And because they're in series, no current will flow, and the output will remain low. If instead we press them both down, it means that both of the transistors are conducting, and we then have a live output. So in order for a AND logic gate to provide a high output, I need input A and input B to both be high. Again, an AND gate can be easily represented for its logic function based on a truth table. The truth table is the single most important aspect when we're dealing with logic gates. There are 4 different combinations. Logic gates can have more than 2 inputs, but only ever 1 output. And so below you can see the different combinations that could potentially occur on this type of logic gate. An OR logic gate also uses 2 transistors, but this one's a little bit different. You'll notice that the way in which the transistors have been connected is they're in parallel. Now, if they're in parallel, that means each one now has the ability to energize the output. It doesn't matter which. And so if we take a look at the symbol is definitely different. It looks like an arrow versus the AND logic gate. And when we look at the operation, I can press down input A or B, and the output will go high. We can even press them both down. And so because of this, the ability to press down input A or input B This logic gate is called an OR gate. An OR gate, again, has 4 different combinations or states. And because of that, the truth table, much like the AND gate, has 4 independent rows. The truth table is the most important aspect, in addition to the shape of the logic gate symbol. Now, even this logic gate that we've looked at, the OR, can have more than 2 inputs, but the same operation would still take place. It wouldn't matter which one had gone high, the output would then go high. Now, there are many additional logic gates that can be created by combining combinations of AND, OR, and NOT gates together. Here I'm going to show you just a couple. If I take an AND gate and I connect it in series with a NOT gate, we end up with something called a NAND gate, which has no relationship to NAND bread. A NAND gate has an A and B, or 2 inputs, and an output. But notice that there is now a circle at the tip of the AND gate. And that's because now if both A and B are high, Y is low, or the output is low. If both A and B are low, that would mean Y would be high. So it's a little bit different in its operation. If I took a standard 2-input OR gate and connected it in series with a NOT gate, we'd end up with a NOR gate. No relationship to Norway. In this system, what we have is again a circle at the tip of the OR gate, which represents the inversion. If either A or B are high, Y is low. If both A and B are low, that would mean Y is high. So it's a little bit different, and it gives you different operations for different types of control scenarios. A timing diagram is a way to offer a visual representation of the operation of inputs and outputs in a logic gate, and we're taking into consideration time. Now, it may seem a wee bit complex when we first look at it, but essentially what's happening is we're showing 1, 2, 3 independent signals. Input A and B are located on the top, and the output, Y, is shown at the bottom. Y is dependent on the inputs being high or low, and that will then depend on the type of logic gate that's used. If we look at a standard AND gate, AND means that both A and B must be high in order for the output to be high. And that means that as we follow along the timing diagram, we want to see that both of them are high, or 1. So for the first time period, they're both high, which means the output should be high. For the second time period, input A is low and B is high. So that means that the output is low for time period 2. Time period 3, they're both high, means they're both going to initiate an output that is high. And then for time period 4, A is high, B is low, and then A and B are both low, which means that the output remains low for both. Let's look at another one. This is an OR gate timing diagram. Again, an OR gate means that if A is high or B is high, the output will be high. So they're both high, which means output is high. Time period 2, A is low, B is high, but that's okay because all we need is one high, meaning the output is high. Time period 3, looks like they're both low, which then means we have a output that's low. And then time period 4, we have a high and a low, so the output is high. Let's look at another one. This is an example of a NAND gate, one of the combinations that we looked at. Now, a NAND gate means that we have both A and B need to be high in order for the output to be low. So if we take a look at the timing diagram, A and B are high. That means we've got a low output. Time period 2, A is low, B is high. Well, we said the output will only be low when both A and B are high. And so this one's a little bit more tricky as we start to interpret how the system should work. A advantage to using the truth table along with this would be seen very clearly what the input and output requirements would be. So when doing a timing diagram, when determining the outputs of a timing diagram, I always say have the truth table available for the logic gate you're interpreting. A is low, B is low, which means output is high. A is high, B is low. Well, looks like we're still high. A is low, B is low, still high. And it's not until both the inputs are high that we have an output that is low. Finally, one last example. This is a NOR gate. It means that if A is high, output will be low. If B is high, output will be low. If both A and B are high, output will be low, which then means if A and B are both low, output will be high. Again, use a truth table to distinguish what's going to happen. In the first time period, they're both low. A and B are low, which means output is high. When A goes high, it means that output goes low. Again, A and B are low, so output is high. When B goes high, output goes low. Again, A and B are low, which means output is high. And finally, when A goes high, output goes low. Always have the truth table handy and available. Although initially it may be a bit confusing, if you have the resource beside you, you can then start to distinguish what the requirements are for the output based on what combination of inputs you have.